Start recording. And we're off. All right, so I wanted to start with something I hadn't had time to get to last time. So just let me recall what we talked about last time in terms of spaces of flat connections and the moment map for the gauge group action and connections. So we have a Lie group, G, and we're interested in a smooth principal bundle for over a compact two manifold. So again, I say two manifold because some people would call this a Riemann surface, some people would call it an algebraic curve, but I'm not using any kind of complex structure, it's just two manifold. Excuse me. So on this principal bundle, and I'll just remind you, I sort of, I'm using the general language of principal bundles here, but this is actually interesting even for trivial principal bundles. So don't think, oh, I don't know any interesting principal bundles, this must be boring. Like, this is still interesting to do on a trivial principal bundle. You have a space of connections. And we saw last time that this is an infinite dimensional symplectic manifold, where the symplectic structure is you interpret a tangent vector to the space of connections as a one form valued in the Lie algebra. You wedge those together. You apply an inner product on the Lie algebra to the Lie algebra part. You get a two form on the manifold, and you integrate it. All right. And this has a group of gauge transformations, which is, remember, it's automorphisms of the principal bundle, which are G equivariant on every fiber. And sort of all of this stuff, what I want to cover today is talking about this in the case of S1, where much of this stuff is much easier. So don't worry too much, but this is sort of the general picture. That we have a group of gauge transformations acting on the connections by pullback. And every connection has a curvature which measures if I have a path in my manifold and I use the connection to lift it, how does it change as I deform the path? And we got to the statement, but not any kind of proof last time of the fact that curvature is a moment map for the action of gauge transformations. All right, so that's sort of a cool fact, but why is it true, right? Somehow we took no time last time, back on Wednesday, to discuss why is this statement true.
Quick question.
Yeah.
I'm sorry. Would you just remind me again why the curvature is the dual of, what's the dual of the Lie algebra of the gauge group, I guess is what was my question.
Okay, so
the curvature.
The point here is the so let me just simplify my life and think that my principal bundle is trivial, and thus just avoids these issues about having to take association bundles for the adjoint action. So in this case, the gauge group is maps from the base into the group, right? So it's just a way of assigning continuously to, or I should say smoothly, to every point in the base, point in the group. And I act on the fiber over that point using that element.
And in general, it would just be a G equivariant map covering the identity, right? From the bundle to itself, covering the identity.
In general,
it's just an automorphism of the bundle.
Yeah, I think I'm trying to think what it would be. I think it would be like a map from P to G that was equivariant for the adjoint, for the conjugation action on G. I think that's right. And it's sort of, you have to sort of twist by the adjoint action. So the way I like to say it is you take the associated bundle to the principal bundle corresponding to the conjugation action of the group on itself, and you look at sections of that. That's the gauge group. But yeah, I'm sure there is a way of, I probably got is the same thing as, yeah. Anyways, all right. So, right, I have a space of maps. So what would be, and of course, if I take the Lie algebra, then that's going to be maps from B into the Lie algebra of G. And if I have maps of a manifold into a vector space, I can think of that as a vector space. So again, let's say smooth, and I'm being very sloppy about functional analysis here. Then the kind of right dual space would be top forms valued in the same vector space. Or I should actually say the dual vector space. So here I'm, in general, the right sort of dual to maps of any manifold into any vector space is, so I'm going to write this in as sections on B of the vector bundle V dual tensor the top wedge power of the cotangent bundle. So the top wedge power of the cotangent bundle, sections of that are top forms, and I can integrate those over the manifold, right? If I wanted to get fancy about this, I would have to say, oh no, I don't want maps from B to V that are smooth. I want L2, right? I want to take the smooth maps and like give those some sort of norm and take the L2 completion. And similarly, then the dual of that as a Hilbert space would be the L2 completion of sections into the dual of V tensored with the top forms. And there's even sort of a more general version of this. Really, I can think of maps from B to V as sections of the trivial bundle with fiber V. So really, this is a statement about if I have a vector bundle, the L2 dual of sections of that vector bundle is dualize that vector bundle, tensor it with top forms, and then you get a pairing, which is pair those and integrate across the manifold. All right. So in our case, the sort of right version of Lie of G dual is G valued 2 forms. So I'm using G, I'm using the fact that I chose a metric on the Lie algebra. So I chose an isomorphism from G to G dual. And then I tensor that with the second power of the cotangent bundle. I take 2 forms valued in the Lie algebra. All right, great. And of course, that's the same place the curvature lands, is in 2 forms valued in the Lie algebra. So that's why at least the spaces involved line up. So sort of, it's the right kind of space for you to interpret curvature as a movement. So, since this is a little abstract, you have to keep track of all these Lie algebras around. I think it's sort of worth explaining just in the case of G equals S1. And if you understand, it's not hard to expand it into the proof for the whole thing, right? Somehow, right? Your Lie group is generated by 1 parameter subgroups. So somehow, like, you should be able to reduce this to the case of 1-dimensional Lie groups. And if you think a little bit, S1 is actually harder than R, because like if you have an R bundle, you can always mod out by the action of Z and get an S1 bundle. So, somehow I'm, again, going to be a little vague about in what sense this is really true. But if you understand the proof for S1, then you understand the proof in general. and basically just like somehow the proof in general is roughly the proof for a one-dimensional Lie group, which is the proof for S1, kind of extended to every line in the Lie algebra. All right, so indeed, let's consider an S1 bundle over a surface. Examples of these do exist. For example, we talked about when we talked about principal bundles, S3, thought of as the unit sphere in C2, maps to S2 with fiber S1, and it's definitely not a product. This is kind of the canonical example of an interesting principal bundle. There are more than this as well. All right. In this case, a connection is just a usual one form upstairs on the principal bundle, but S1 equivariant, such that when I look at the vector field that generates the S1 action, the pairing is 1. Right? I can take that vector field, I can pair it with my one form, and I get the number 1. And since it's S1 equivariant, on the other hand, if I take the Lie derivative of this connection form with respect to that generating vector field, I get 0. All right, the gauge group in this case. So when you have an abelian group, acting with group elements is an automorphism of the fibers. So your gauge transformations are just specify on each fiber which group element do you act with. It's only with non-abelian groups that you have to be more careful about the definition. So the gauge group, it really is maps from B to S1. And yeah, this is all I'm saying is F acts with the S1 action on each fiber. You do have to be really careful about signs here. Unfortunately, there are like a ton of different places where you can make some sign choice and mess things up. Like, you know, you can always switch the orientation on your surface. There are just like tons and tons of places where you make some choice about signs. I'm not sure I'm totally happy with Canis de Silva's, because I really kind of think this should have an inverse on it, but it's one of these things where like, if you change that sign, well, you can change a sign somewhere else randomly to make everything work out, but I think it just makes life too complicated. Like there's a bunch of complicated stuff about like some people prefer to define principal bundles as right G spaces because then it's, you know, somehow a little more natural. You don't have to take an inverse somewhere that you do if you define them as left G spaces. So it's just kind of, you just always have to be careful about this left versus right and inverses versus non-inverses stuff. All right. So the way that a gauge transformation changes the connection, and you see immediately, oh shit, you have to watch out for inverses. You can pull the connection form back by the transformation where I take the inverse of each group element at each point. So right, if I had stuck an inverse up above, then I could get rid of this inverse here, but I think it's better to just match Canis de Silva. The reason it's sort of nice to have that inverse there is that means that when you look at these sort of calculations with the junctions, when I push a vector forward of this gauge group action by F, and I pair that with the pullback by F inverse of the connection form, then I can use a junction to turn that push forward into a pullback on the other side. And now I'm pulling back by F. I just pulled back by F inverse, so those cancel. Right? So actually, this is exactly set up so that if I take the kernel of this pulled back connection form, which remember is exactly what we're interested in, that's the horizontal space. That's the same as if I had taken the original horizontal space for my connection A and push that forward by the derivative of f. And again, it's just like, you just have to be careful about how everything works out. Here you have to put in an inverse to make sure you get an action that kind of behaves the right way. And it's especially dangerous with abelian groups, because with non-abelian groups, if you don't put an inverse in the right place, you'll realize oh shit, this isn't working out. I wanted to get a left action and I'm getting a right action. But with abelian groups, you don't have that kind of sanity check. So it's unfortunate. Okay, so how do we think about how one of these gauge transformations changes the connection? So if I had acted by a constant function, then I would have just rotated all of my fibers, and by S1 equivariance, my connection wouldn't have changed. So the sort of difference between how the connection changes, you have to look in some direction and see, how does the amount of twisting change as you move in that direction? And well, you can sort of do a calculation here. If you think through, it's not so surprising. So everywhere I'm identifying S1 with R mod 2 pi z. So I can think of F, my gauge transformation, as R 2 pi z, R mod 2 pi z valued function, and I can take its derivative, right? And that actually is well defined. I don't have to worry about the mod 2 pi z because that's a discrete thing. It's not going to change the derivative. So I can always lift that up to a function to R. There are different choices of lifts, but they all have the same differential. So exactly how I'm changing depends on the differential of f. And if you write it out in terms of the connection form, what you get is this pullback is A minus the pullback of df. And this is, you can derive this. Somehow this is not surprising, but you have to kind of think oh, how do I actually check that? And you have to actually look at what the derivative of T of F is, right? Along the fiber, it's just the action you expect, but then transverse to the fiber, you get some extra contribution depending on how F changes. And you can see it exactly has to do with the Lie derivative of F along the direction transverse to the fiber that you're pushing, which you can then rewrite in terms of df. And so you can see this is the change of the connection form. And again, there's some sign that shows up. You have to make sure you do that right. If you change a sign somewhere else, this sign will change as well. All right. Now I have to think about, I'm supposed to, so this is the formula for my action. I now have to think about, okay, when I translate this into a statement about moment maps, what I have to think about is what's the vector field on the space of all connections that I get by taking the derivative of this action, right? So this is like a little bit confusing, but first I'm going to note, since I'm thinking of S1 as R mod 2 pi z, the exponential map is not an exponential. I got rid of it by writing S1 as R mod 2 pi z instead of as unit length complex numbers that I would get by exponentiating I times that. So the exponential map as defined in like the abstract theory of Lie algebras and Lie groups is just the obvious map from R to R mod 2 pi z. So when I look at the associated vector field on the space of connections, it's actually just the constant vector field given by minus df. So thinking of minus df as a one form gives me a tangent vector to the space of connections. And if I integrate that vector field, what am I going to do? I'm going to move in constant speed, subtracting df from things. And that's also what the action of my gauge group does. Right? So if I think of an element of the gauge group as the exponential of a function into my Lie algebra, that just means choose a lifting to R of the function. And so it all works out. So I actually have a very simple form for my action. It's just minus df, which I have to remember is a vector, a tangent vector to the space of connections. Okay, well, now I want to check that I get the properties of a Hamiltonian action. I don't know why this is so slow, specifically when I'm sharing. Never had this issue other times. Okay, so let me just remind you, I'm hoping that I will get the relation that when I take some f in the Lie algebra of my gauge group, and I pair that with my moment map. So with the curvature, think of that as a function on the space of connections, take its exterior derivative, that will be the same as contracting with respect to this guy, which Canis de Silva would call F sharp, minus df thought as a vector field with the symplectic form. So this is the property of being a Hamiltonian vector field for the function of taking the curvature. So that means kind of a natural thing to compute is I take this vector field, it's constant vector field, and I contract it against the symplectic form, and I get a one form on the space of connections. So I'm going to think of that as something that eats tangent vectors to the space of connections. So one forms. Let me just emphasize this as a one form, which is the same thing as a tangent vector to the space of connections. And I want to contract that in the symplectic form with minus df. I'm now worried that I've gotten the ordering wrong, but well, we won't worry about that. I'm now slightly worried about whether I got the signs right here. That's just an occupational hazard. So that means I take alpha, I wedge it with minus df, and I integrate that over my two manifold. And when I see something like alpha wedged with minus df, that seems very suggestive, right? I have a formula, which is that if I take the exterior derivative of f times a, and of course now I'm thinking of these as forms on b, I'm taking the exterior derivative on b, that's df wedge a plus f dA. right? So when I integrate A wedge minus df, I can rewrite that. Okay, I think I found my sign error and I can actually fix it. I think that minus sign shouldn't be there because I should actually be taking these in the opposite order. Minus df a. So I put these guys in the wrong order, and I'm getting rid of a minus sign to correct for that. Similarly here, these guys, I always forget that you can't see if I point. These guys are in the wrong order compared to the function I have above. So this is really minus df wedge a. All right. So on the other side, I'm going to have minus d of fa plus f times dA. And of course, this first term, minus df alpha, I'm integrating over a closed two manifold, over a compact two manifold. So it's just zero by Stokes' theorem. So this is by Stokes. And this is just integration by parts. And this reminds me, as I look at this and ponder where to put, whether I need an apostrophe, that we once had a 10-minute long argument in a faculty meeting about where the apostrophe in Stokes' theorem goes. I think we ultimately decided that we didn't need one. Anyways, so there's a natural way of rewriting this inner product that sort of emphasizes F and A in a different way. And this is going to be key to understanding this moment map relation. This integral of F dA is going to show up on the other side of the moment map relation. All right. So on the other hand, the other thing I need to do is I need to take F and take its inner product with the curvature. Well, it turns out in the S1 case, curvature is very easy to compute. It's just the exterior derivative of the connection form. That's trivial along the S1 direction, so I can actually think of it as a form downstairs on B. All right. And when I want to compute the inner product of an element of the Lie algebra with the curvature, that's just the integral over B of F dA. Now you may say, wait a second, you don't get to use Stokes' theorem there because A isn't a form on B, it's a form upstairs on P. And you're right, but of course I don't want to look at the curvature of one connection. I want to look at how this function changes as I vary the connection. So I want to look at this function, which I'm not going to try to apply to Stokes to, or try to match with the previous thing. I'm going to take this function and take its differential. Think about how does it change when I move along some vector field, some vector to the space of connections. Again, space of connections is affine, and this is an affine function. So if I have two different connections, I can take the difference between them. That's the one form downstairs. So now let me actually say this a little more carefully. Jesus, it's so hard to add space. Right, so note, if I have two connections, the difference between them this is now effectively in a one form on the base, right? Since the inner product of the connection with a vertical vector is specified by being connection form is always one. When I take the difference, I get something that is perpendicular to every vertical vector. So it's pulled back from downstairs. Maybe I should have written this differently. So this is going to be equal to the pullback of some alpha, which is a one form downstairs. So when I want to move along some tangent vector and take the directional derivative in that direction, that tangent vector comes from a one form. And of course, what this formula upstairs tells me is that exactly what I get is that when I move along the direction of a one form, the derivative in that direction of the pairing is of the pairing of curvature with F. So what I'm doing here, what I'm really writing is, this is the Lie derivative along A thought of as a tangent vector of the pairing of F with curvature. And I found that this is the same as putting into the symplectic form minus df. Okay. And this is just another way of rewriting the moment map relation. Right. So the Lie derivative with respect to A, that's the same as contracting against A, the differential of F curve. And on the other hand, this is contracting against A, the contraction against minus df of the symplectic form. So these two expressions are what the symplectic form is trying to, the moment map relation is trying to show are the same. And I've seen that I get the same answer for contraction against any tangent vector. So that means they're the same form. All right, so this shows that curve is a moment. All right, are there any questions about this? Okay, hopefully this illuminated something. And this is, I think this is sort of an interesting subject, but we don't necessarily have time to do it justice. There are kind of various other interesting directions you can go if you're interested in, you know, the topology of surfaces, understanding their fundamental groups and the space of representations. So I don't know, if anybody feels like doing non-abelian Hodge theory for their project, that would, you know, this is one very small piece of that.
I have a small question. Does this generalize in any way to higher dimensions? Because you know, the fact that you have a surface is you need to use that. Your pairing on connection forms, right? It gives you a two form. To get a number out of it, you need to, you know, feed it the fundamental class or whatever. You need to integrate over the surface to get a number, to get a symplectic structure, right? So
yeah.
So does this have any higher dimensional generalizations?
Yeah, so this is actually something which I have somewhat tried to figure out. And yeah, I wasn't able to find any sort of good source on it. So, I mean, this is the two-dimensional version of much more general story, which is Yang-Mills theory. So, you know, you can interpret all of this as being about doing field theory where the Lagrangian is the norm squared of the curvature of the form. But I wasn't able to find sort of a good resource on how that all hangs together. So there are interesting higher dimensional generalizations of this stuff. But I will probably say something dumb if I try to say anything extremely specific about them. I sort of looked for some good sources and didn't find much. Unfortunately, like Yang-Mills theory is like a very big subject, so it's sort of
I've heard the term. So yeah, I guess there's stuff to look at for sure, but
yeah. I mean, I think some of this is like, there's a lot more stuff out there about the quantum version of it because that's more interesting. So I mean, this is mostly based on sort of an old paper of Etienne Bach. I don't think they really say very much about the higher dimensional generalization, but it's sort of, you can, yeah. So let me just say that, and we'll.
All right. Can I ask one other random question? So this says that the space of connections is a symplectic manifold, right? Mm-hmm. If I give you a Hamiltonian, can you tell me what the flow is? Like, let the Hamiltonian be, take trace of the curvature of a connection. What's the Hamiltonian?
Is trivial on the reduced space, or you mean on the whole space?
Yeah, on the whole space. Yeah. Oh,
yeah,
you're right.
We're taking. It tells you it's you. Yeah. I guess it depends what you mean by trace, but.
Okay. Anyway, I'll think about it some more. But
right. I mean, like, if you go through this set of formulas, well, in some cases you'll be able to make sense of things, and in some cases you won't. Right. Like.
Oh yeah, I forgot what you said before, that we were taking the zero level set of the moment map and then looking at the reduced structure on that and getting something finite dimensional, and that was sort of like the more interesting invariant. So
I think so. I mean, there in theory you can get some interesting flow on the space of connections from any function on connection.
Any function you can cook up, right?
Somehow like seems like it could get kind of complicated, right? So what you're going to have to do, you have your function, you're going to have to look at how does it vary as I change my connection, right? Mm-hmm. And for the curvature, the way it varies is pretty simple, right? It's just sort of pairing your, taking, somehow like another way of saying this is that like, it turns out it's very simple. What happens in this specific case with taking linear functions of curvature. If you take some nonlinear function of curvature, it could be much more complicated.
Thanks.
Yeah. All right. So that's sort of one interesting moment map. And now I want to kind of switch gears. This was stuff that I kind of intended to cover on Wednesday, but maybe not so surprisingly, I didn't have time. So I wanted to talk about one more situation. Probably not just one more, but certainly another situation where this notion of reduction and Hamiltonian actions is very interesting and useful. And that's this world of symplectic toric. Those of you who know a little bit of algebraic geometry, these are the same thing as smooth projective toric varieties. And I will probably slip sometimes and call them toric varieties because that's sort of something that's, I think, a more standard notion in the literature, but we're in the symplectic world. And there is some, tiny little bit of interesting, difference between the algebraic geometry perspective on things and the manifold perspective on things. But if you hear about toric varieties in the future, this is roughly the same thing, or at least one special case of them. And the reason that they're varieties is they all have Kähler metrics, which make them projective with the induced complex structure. That's something that, at least today, we won't talk about really at all, but it is the truth. So what is a symplectic toric manifold? It's a compact symplectic manifold, M omega, of dimension 2n, equipped with a Hamiltonian action of a torus which is half dimensional. So dimension n. Now, this is the biggest torus action that you can have, which is Hamiltonian. So since the torus is abelian, that means that the kernel of the derivative of the moment map is coisotropic at any point. So that was something we had seen for the zero level of the moment map. For abelian things, all levels behave like the zero level. For non-abelian groups, this is very much not true, right? For non-abelian groups, you have, for example, coadjoint orbits. And those have dimension less than the group, but they have an interesting non-trivial action on them. But unless they're a point, their moment map doesn't hit any point that's stabilized by the coadjoint action. Right? So I'm really using the fact that the moment map level is fixed by the coadjoint action. So I'm using the fact that the group is abelian. So for non-abelian, coadjoint orbits are counterexample. Oops. Right. Cool. So if you sort of think through what this tells you, if you have a symplectic manifold that has a Hamiltonian Tn action, should have added Hamiltonian here, then the dimension of the kernel of this derivative, well, it's less than, that dimension is greater than half the dimension of m, because it's coisotropic. But on the other hand, this is the kernel of a map from the tangent space of M to the tangent space of Tn. So the biggest the kernel could I have this wrong? Right. All right, just having this like, wait a second. Right, because the kernel could be bigger than that. Well, anyways, I have apparently screwed this up, but you do conclude that M has to have dimension greater than 2M. What did I do wrong here? Well, there's some sort of dumb mistake here, but I'm not seeing what it is at the moment. Anyways, trust me that if you do the algebra correctly, you will conclude that dimension of n has to be greater than or equal to 2n. All right, so symplectic toric manifold is a compact symplectic manifold that has the biggest possible action, has as great a dimension as it can possibly have. And well, that's sort of, I don't know, that's a very general thing, just has some action of some group. But on the other hand, it's a very powerful thing because that action is really big. The orbits are, they're half dimensional, but somehow they have very powerful control over the manifold. And it turns out that there's sort of a surprisingly simple classification of these. So in order to talk about this, we're going to have to talk about some combinatorics because They're classified by combinatorial objects. And the objects we're interested in are convex polytopes. So that's a bounded subset of Rn. People will argue about whether convex is part of the definition of a polytope. People will also argue about whether being bounded is part of the definition of a polytope. Well, I'm interested in polytopes that are bounded and convex. So it's a bounded subset of Rn, which is an intersection of finitely many half spaces. So we have these linear inequalities of, I have a point in Rn and its pairing with some other fixed vector is less than some fixed real number. So all half spaces can be written that way, and everything of that form is a half space. So I have some list of VIs, which are going to be normal vectors to faces of my polytope, and I have some lambda i's that sort of tell me exactly where those faces are. So maybe I will draw a picture here. So I will have some picture like this. In each one of these bounding, so each piece of the boundary is part of a hyperplane, and that hyperplane is defined by inner product with some normal vector to it. Right, so I think my 136 students learn this as the scalar equation of a line. And note here, because I define this using the less than inequality, my normal vectors are always pointing out of the polytope. That's a little bit arbitrary. I think I changed my mind twice about which direction these inequalities should go. It just kind of depends on how you want the conventions to work out later on. Hopefully I did it right. Okay. So we're going to want polytopes that have some special properties. One of those special properties is that they're rational, which for me means that Vi, the vector Vi, the normal vector, is rational. So in this picture of a polygon, this would mean that all of these lines have rational slope. However, I'm not assuming that lambda I is rational or has any other property. It can be any real number. And of course, without loss of generality, I can assume that actually my VIs are in Z to the n. Just by multiplying them by a scalar to clear out the denominators. And there's sort of a natural way to do this, which is to require them to be primitive in Zn. So the entries have trivial greatest common denominator. Or put another way, it's not an integer multiple of another element of Zn. Right. And this is actually unique if I require it to point in the correct direction. Right? I should only multiply my my VI by positive real numbers, because if I multiply it by a negative real number, I'll mess up this inequality. So there's a unique positive rational number that clears out the denominators. I multiply by the LCM of the denominators. The face of my polytope is a subset of Rn. So note here, face is a subset of Rn. It's not a set of the vectors Vi, but it's a set of Rn, which is the solution set of some of these equations. So I have the equations x with Vi is equal to lambda I, and I look at systems of those. And I'm looking at the solutions which lie in my polytope. So for example, in this example, So this is a face. It's the solutions to the equation for V2 that lie in my polytope. This is a face. It's the solutions to the equations for V3, et cetera, these guys. And then if I take two of these hyperplanes, I get the vertices. And you'll note here, you might say, well, what about the common solutions to the equation for V5 and V2? Well, there are some common solutions. There's a common solution out here, but it doesn't lie in the polytope, so that's not a face. All right, and a vertex is a zero-dimensional face. A facet is an n-1 dimensional face. I'm not sure we're actually going to say anything about facets, but these are good terminology to know anyways. One property we'll want from our polytopes is that they're simple. So that means at each vertex, there are exactly n facets needed. So note here, a vertex, since it's zero-dimensional, it has to be defined by at least n equations. And this says, well, there aren't any equations beyond the n. There's a unique set of n equations that the vertex satisfies, and no other equations that come from facets of your polytope. So for example, here, that's fine, right? Each one of these vertices is defined by exactly two of the equations, and it doesn't satisfy any of the other ones. Somehow in 2 dimensions, this is a dumb condition. It's not interesting. But in 3 dimensions, it becomes a serious thing, right? So here I have this vertex. It satisfies 4 equations coming from bounding hyperplanes of the polytope, right? So I know I didn't draw this great, but this is like the top of the Great Pyramid of Giza. There are 4 hyperplanes that meet there. And so between the normal vectors of those hyperplanes, there's a linear relation. So another sort of way of saying this is when you look at the hyperplanes of the normal vectors, the hyperplanes going through your vertex, they form a linearly independent set. And note here, if I just sort of jiggle my lambda i's, well, I'll sort of break up any linear dependence. And I'll end up back at a simple one. So for example, with this pyramid example, if I jiggle my lambda i's, this vertex will break up into a line and 2 vertices, both of which actually do satisfy the simplicity condition. All right, cool. So for the moment, that's just a condition that a polytope might have. It might be rational, might be simple. We call polytope Delzant if it is rational, simple, and there's one extra condition which we call smoothness. And basically what this says is if I look at one of my vertices, so by the simplicity assumption, this has n edges coming out of it, one-dimensional faces. And if I move my vertex to the origin, so for example here, I move my vertex to the origin. Oh, I didn't do that perfectly, but fine. I look at the edges coming out, that in those lines, there is a basis of Zn. So this requires smoothness. This last condition is really a bit strange. I feel like Kenneth de Silva's description of it is a little ambiguous. The way I sort of like to say this is that the being simple means that if you look at a little neighborhood around your vertex up to translation, it looks like I take the negative orthant. This has to do with this thing about like I was taking less thans. So all of the vectors in Rn with non-positive entries, and I apply some element of GLNR to that. I apply a linear transformation to that. It gets somehow sheared and twisted and moved around, but it still has those n vectors coming out and bounded by n hyperplanes. And the Delzant condition is that I can do this with an element of GLNZ. So note here, the element of GLNZ, the matrix that does this, its columns are a basis of Zn, and that's the basis of vectors that live in the edges. I kind of actually prefer to think of this dually as saying that the normal vectors to the hyperplanes form a basis of Zn, and if you think in terms of this matrix A, those are the rows of the inverse matrix. So there's some duality here, right? Of replacing A by its inverse transpose. So I could also sort of dually look at this point, look at the two normal vectors. I guess what did I do? That. No, anyways. Look at the two normal vectors and ask whether those, in this case, are a basis of Z2. And I'll note here, right, because I am not assuming that my lambdas are in Q. So being a Delzant polytope, it's purely a property of what neighborhoods around individual vertices look like. And I'm free to kind of stretch and shrink my polytope continuously and have lots of like irrational length distances between things. But it's sort of the angles at the points where hyperplanes meet, or more generally at vertices, that determine whether something is Delzant or not. All right. So this leads us to theorem of Delzant, that if we have a symplectic toric manifold, so it's got a moment map by definition, so I can look at its image under the moment. And that image, identifying the dual of the Lie algebra with Rn, is a Delzant polytope, and two symplectic toric submanifolds are equivariantly symplectomorphic if and only if the two polytopes differ by a translation. And maybe I'll note here, for those of you worried about this, wait, did I make some weird choice when I chose the isomorphism from the dual of the Lie algebra to Rn? Inside here, inside the dual of the Lie algebra, are the elements that integrate to actual characters on the group. So there's a distinguished lattice called the weight lattice inside the dual of a torus. And that should be sent to Zn. And of course, any two different ways of doing that will differ by an element of GLNZ. So in particular, acting by GLNZ will preserve being a Delzant polytope. All right, good. And note here, of course, since my moment map can be arbitrarily shifted by an element of the dual of the Lie algebra, the thing that's really attached to, if you only remember the T action and not the specific moment map, is only the Delzant polytope up to translation. Should I take a break? I don't know, are there any questions?
Yep. So does the this translation that sort of characterizes the symplectomorphic classes of these toric manifolds, do they have to be like integral translate, like lattice translations, or does it have to be? It doesn't have to be lattice translations?
No, because I don't. So I can just take the moment map and add a completely arbitrary element of T dual to that, and that will again give me a moment map.
Right.
So like that shows you, if I have one polytope that shows up as a moment map image of a symplectic toric manifold, all of its translations are also moment map images for the same symplectic toric manifold, just under different moment maps. So there's no kind of way that things get more down.
Right. Because I was thinking that like maybe if you just translate arbitrarily, maybe you sort of come back to the original manifold or something, like there's a fixed point or orbit of some kind, but
I mean, it's the same manifold, right? If all you're doing is translating, it's the same manifold, same action, you're just picking a different moment, right? So I'm sure I have this example somewhere further down, but the most basic example to think about is if I have S2 with the usual rotation S1 action, right? So that's a symplectic manifold. I have an S1 action on it that's half the dimension. And we know what the moment map is. It's the height function. But I'm being a little vague here, right? So the height function, so H, which I'll just define to be the height function, is a moment map for the symplectic form omega equals dH d theta. So this is like the standard area form on the sphere. But, well, H plus any random real number lambda is also a moment map.
right. On S2.
For the same omega. But the other thing is that for mu, any positive real number, mu times H, I hope that I'm going to get this right, plus lambda is a moment map for mu times omega, which is also a perfectly valid symplectic form on the two sphere, right? So in R, any closed segment, so any A to B, is Delzant. And the corresponding M is always S2, but which symplectic form on S2 depends on how long the segment is. That was, B minus A. Well, I'm just worried that I'm getting off by factors here. It's probably over 2 times omega, since I just, I haven't worked out this example carefully. So kind of everything here is like, oh, there might be a factor that's off somewhere. But, so every one of these segments always corresponds to an S2, but it's with a different symplectic form for different lengths of the segment. And so there's no condition on A and B. They can be anything. Because, somehow the Delzant thing is something about how like slopes meet and there are just no slopes in R. There's nothing to worry about there. Okay?
Yep. Okay. Thank you.
Great. Oh, yeah. Of course, that was the next thing. So another way to think about this action on S2 is that this is CP1, and you're acting with multiplication by diagonal unitary matrices. And I'm not, CP1, that's the projectivization of C2. So 2 by 2 complex matrices act on that, but scalar matrices act trivially. So I might as well just assume that the last entry along the diagonal is 1. And then I'll get a faithful action of an S1. And writing it this way is nice because then I can increase the dimension and do roughly the same thing. So I can take CP2 and look at e to the I theta 1, e to the I theta 2, and then 1, because if I vary what that last entry is, my action won't be faithful anymore. And when I let that act, that corresponds to a Delzant triangle in R2. And there's actually only one way of making a Delzant triangle. So if I have a triangle that's Delzant, I can move one of the vertices to the origin and make 2 of the sides the X and Y axes. And then you can check that the other edge has to be given by either X plus Y is constant or X minus Y is constant. That corresponds to the 2 different orientations on CP2. I think, anyways, yeah, so that's the only possibility. Actually, sorry, what I actually should have said is that either X plus Y is constant or X minus Y is constant, and those 2 differ by an action of GL2Z. So it doesn't matter which one you choose, they always give you CP2. And well, I could tell you, this is an exercise, go write down the moment map for the action of this guy on CP2, and you'll see that this is the image. I prefer to think about this as, so there's sort of lots of stuff that I'm kind of secretly doing in my head about how these work. Let me let you in on sort of one of the secrets. Every edge in your polytope is going to have an S2 sitting above it. And the slope that that guy is going to point along comes from your torus is going to act on that S2, factoring through an S1. And you're going to look at the perp to the kernel. So I have a kernel that's n-1 dimensional. Its perp will be a 1-dimensional subspace in the dual of the Lie algebra, and that's the direction my edge points. So for example, in this case, right, there are 3 torus invariant S2s. I'm going to call these lines because I'm used to thinking in terms of algebraic geometry. So these are CP1s inside CP2, which are invariant under the action of the torus. So there's the x-axis, there's the y-axis, and then there's the line at infinity. And you can look at how the torus acts on these, and the kernels are given by, either you forget theta 2 when you act on the x-axis, you forget theta 1 if you act on the y-axis, and you only remember the sum of theta 1 plus theta 2 when you look at the line at infinity. And when you take the perps to these, right, I'm getting, here's 1, 1, here's, okay, it's 0, -1, because we want to get the sign right, -1, 0. So these lines correspond to, let me get this right. So this guy is the x-axis, slightly confusingly because I'm taking perps. This is the x-axis. And this guy is the line at infinity. All right, cool. So when I draw the moment map image, I just take the perps. All right, maybe the next kind of interesting 2-dimensional example. Well, there's one that maybe I will just mention quickly. If I can take CP1 times CP1, and then I get a square. So when I take the product of two symplectic toric manifolds, I'm also taking the product of their corresponding polytopes. So the square is the product of two segments, so it corresponds to two CP1s. And of course, I can make this a rectangle, lengthening it in either direction, and that corresponds to choosing different symplectic forms on the two factors of CP1. All right. One more slightly more interesting example is this guy. Now, according to this theorem, I can just tell you this polytope, convince you that this is Delzant, and then the theorem will automatically construct a manifold of this form. And sure, looking like we'll talk about the proof next time, which is fine. So let me just tell you, the manifold that comes out of this guy is always CP1 connect sum with CP2 connect sum with CP2 with the opposite orientation. So, right, let's think about, okay, I just drew a picture here, but of course, whether this picture is Delzant or not is going to depend on what the angles are. And in particular, it's going to depend on the slope of this guy. So all of these edges are fine. They have normal vectors. 1, 0, 1, okay. So at these vertices, the smoothness condition is fine, but whether smoothness is going to hold at these vertices depends on what the slope of this other edge is. And the key thing we need is that the slope is -1/n for n a positive integer. So if we write this in terms of normal vectors, right, the normal vector to this horizontal edge is 0, 1. So I need the normal vector to this guy to be something that gives a basis of Z2 with 0, 1. Well, so its x coordinate had better be 1. Can't be 12 or 17 or whatever, because then I would never be able to get x coordinates that aren't divisible by whatever the entry there is. And since it's pointing upward, it has to be positive. So it's 1. Oh, sorry, it's not that's pointing upward, it's that is pointing rightward. So it must be 1. And then the y coordinate can be anything, right? I can always subtract multiples of the other basis vector from it. That's fine. So I'm going to get lots of different possibilities, but they all have this integrality condition for the slope. All right. So many possibilities. The other thing is, as I mentioned, you sort of see here this behavior of you can kind of stretch, right? So I can scale the whole thing, but I can also change the relative length of the horizontal and vertical distances with respect to each other. And as long as I'm keeping the slope fixed, that's actually always just adjusting what the symplectic form on my manifold is, on the same underlying manifold. Sorry, with the same underlying torus action, I should even say. Whereas, yeah, what happens when I change the slope is a little more complicated. It still doesn't change the diffeomorphism type, but it's weirder. All right. If you do like thinking about algebraic varieties, I can think of this as a blow up of a weighted projective space. So I'll this, but if I take something like this, where here I have slope 1/n, what's going to happen is my smoothness condition is going to be violated. So here I have 0, -1. Here I have -1, 0. Here I have 1n. And you'll note here my smoothness condition gets violated. We'll see later on this corresponds to, I can construct this as some sort of quotient of a torus action, by a torus action, and there's a finite stabilizer at points where the smoothness condition fails. So what happens here is this guy is perfectly well defined as a symplectic orbifold, or as an algebraic variety, for example. And I do a construction at this non-smooth point called blow-up, which gets rid of the lack of smoothness and turns it into this guy. And for those of you who know about blow-ups, right, if I blow up P2, I'm inserting an exceptional P1, and that's this P1 coming from this segment in the boundary of the polytope. All right. So higher dimensional examples are harder to draw. You know, there are lots and lots of them, but it's hard to like actually draw pictures of them because they're like 3 and 4 dimensional. One that's definitely worth knowing is sort of dimensionally upgrading the story about CPN. So in that case, you know, just as before, you have the diagonal unitary matrices and just leave off the last coordinate. This is the, excuse me, the torus of PUN, the projective unitary group, the image of the unitary group acting on projective space. And you're always getting a simplex. So you take an orthant. I guess I wrote the positive one, even though I should be taking the negative one, but it doesn't matter, you get the same space. So you take the coordinate hyperplanes and then one extra hyperplane that comes from the sum of all the coordinates. And you get this sort of simplex picture. So in 3 dimensions, it kind of looks like, ooh, it's a little slanted, but that's okay. Let me use a different color. It looks like this. So I have facets that come from all the coordinate hyperplanes and then one facet here coming from the sum of all the coordinates. All right, so that's sort of the examples. I'm running really low on time, so I'm sort of like, is it worth saying anything about the proof? Yeah, let me get the details later. Let me just try to kind of explain the idea of the proof. And we'll talk about this more next time, or at least the idea of the construction, let's say. So one part of this is proving that if you give me a Delzant polytope, then I can construct a symplectic toric manifold with that Delzant polytope as moment mapping. And the rough idea is this. The polytope delta can be written as, so you can always write any polytope as the intersection of this negative orthant in some higher dimensional Rn so I can write this in some RD, the intersection of all the points where all the coordinates are negative, intersected with an affine subspace. So for example, which is isomorphic to my original Rn. So unfortunately, like, you can only really draw this very effectively in very low dimensions. So for example, if I want to construct the line segment in this way, I take R2. So here I have my negative orthent. And then I take an affine subspace like this, and indeed, the intersection of that with the negative orthent is a line segment. I can upgrade this a little bit, right? So the simplex that we talked about for CPN is relatively easy to construct this way. So for example, if I upgrade to 3 dimensions, so let me make the stuff that's closest to me on the bottom, the negative orthent. Right. If I then cut a hyperplane through here like this, oops, then that will slice through that negative orthent, and its intersection with that guy will be a simplex. In general, this is a bit harder to draw because the dimension of the space you need is the number of bounding hyperplanes. So in general, what do you do? So, you know, I want to have an example like this guy. So a polytope like this is always defined, as we've discussed, by saying I have some linear function, v1. So the linear function is xv1, xv2, xv3, xv4, corresponding to the different perps here. Right, and these have to be smaller than or equal to -1, -2, -3. All right. Well, I can send X to the element of R4 given by λ1 v1 minus λ1. X2 v2 minus λ2, etc. All right, so this maps R2 into R4. And note it's not a linear map because I have that minus λ1, minus λ2, minus λ3, etc. So this is an affine map. Which means if you look at the difference between where it sends 2 points, then like, yeah, let me not actually, yeah. That if I look at where it sends the origin and subtract that off, it becomes a linear map, but it's not actually a linear map. But its image is an affine subspace, and this is going to exactly send my polytope to the intersection of that affine subspace with this negative orthent. So my polytope delta maps to this guy intersected with the image. All right, so that's some fun combinatorics, which gets us started. But the key point here, and I'm almost out of time, so I'll just discuss this next time. Symplectic reduction. So this guy O minus is the image for the moment map of CD with TD acting on it in the obvious way by multiplying coordinates by unit length complex scalars. This moment map, this is a map from CD to RD that sends Z to -1/2 times the norm of Z1 squared, the norm of Z2 squared, etc. And this minus, the fact that I've been using the negative orthant everywhere is because there's a minus sign here. And if I had changed my conventions about this torus, I would be able to get rid of that minus sign and use the positive orthant. And intersection with an affine subspace has a natural interpretation in symplectic geometry. It's symplectic reduction for a subgroup. All right, well, it's exactly 2:30, so we'll discuss how to, what exactly I mean by all of this next time, but I just kind of, I don't know, next time, if you do this all at once, you're just kind of throwing all this combinatorics at people. So I want to just kind of mention this combinatorial setup, and we'll talk next time in a little more detail about how that works. All right, are there any questions?
Yeah, I got one. We talked a while back about Liouville integrable systems, which I believe can be thought of as systems with a torus action that's, half dimensional. Do those give examples of these types of things? Like, is there anything you can say about, what is the moment map for such a torus in terms of?
So these are examples of integrable systems.
Okay.
Right. So here, the key difference here is that if you have an integrable system in the usual sense, right? So what that gives you is an action of R to the n. If the
right.
n functions in it. And usually the orbits for that will close up. In sort of nice cases, the orbits for that will close up, and each individual orbit will be a torus. But they won't all close up at the same time, so it won't be a torus action.
Oh, I see.
So an example that had come up in some conversations I was having with you is, what if instead of, -1/2 Z squared on C, this is from C to R, generates the S1 action on C by unit complex numbers. Yeah. What if I didn't have that squared there? What if I took minus the absolute value of C? Well, of course I would have a problem at 0.
Right.
That would be rough. But what happens otherwise? So what this gives me is the Hamiltonian vector field is always unit length. right? Basically, because the derivative of the absolute value is always sort of unit length. So the Hamiltonian vector field is still tangent to.
But you're not going to get one nice rotation, like the speeds won't match up nicely.
Exactly, circles of where this distance is constant, right? Like the level sets are exactly the same.
Yeah.
So in fact, the orbits of the Hamiltonian vector field are exactly the same because in 2 dimensions, those are exactly the level sets, but always has unit length. So you traverse these level sets always at unit speed. And so indeed, they like never close up at the same time, even though individual one is a circle.
I see. So this one doesn't have a torus action. Basically.
Right. So getting a torus action is something really special. Like there are many more integrable systems than there are of these symplectic toric manifolds.
I see. Great.
So
Thanks.
this is sort of a particular really nice example of a system.
Gotcha. Thanks.
Any other questions? All right, then I will stop recording.